In computational complexity theory, QMA, which stands for Quantum Merlin Arthur, is the quantum analog of the deterministic complexity class NP or the probabilistic complexity class MA. It is related to BQP in the same way NP is related to P, or MA is related to BPP. Informally, it is the set of decision problems for which, when the answer is yes, there is a polynomial-size quantum proof which convinces a polynomial-time quantum verifier of the fact with high probability. Moreover, when the answer is no, every polynomial-size quantum state is rejected by the verifier with high probability. More precisely, the proofs have to be verifiable in polynomial time on a quantum computer, such that if the answer is indeed yes, the verifier accepts a correct proof with probability greater than 2/3, and if the answer is no, then there is no proof which convinces the verifier to accept with probability greater than 1/3. As is usually the case, the constants 2/3 and 1/3 can be changed. Changing 2/3 to any constant strictly between 1/2 and 1, or changing 1/3 to any constant strictly between 0 and 1/2, does not change the class QMA. QAM is a related complexity class, in which fictional agents Arthur and Merlin carry out the sequence. Arthur generates a random string, Merlin answers with a quantum certificate, and Arthur verifies it as a BQP machine. Definition: a language L is in if there exists a polynomial-time quantum verifier V and a polynomial P such that there exists a quantum state such that the probability that V accepts the input is greater than. For all quantum states, the probability that V accepts the input is less than, where ranges over all quantum states with at most p qubits. The complexity class is defined to be equal to. However, the constants are not too important since the class remains unchanged if n are set to any constants such that is greater than. Moreover, for any polynomials, and we have problems in QMA. Since many interesting classes are contained in QMA, such as P, BQP and NP, all problems in those classes are also in QMA. However, there are problems that are in QMA but not known to be in NP or BQP. Some such well-known problems are discussed below. A problem is said to be QMA hard, analogous to NP hard, if every problem in QMA can be reduced to it. A problem is said to be QMA complete if it is QMA hard and in QMA. The local Hamiltonian problem. The local Hamiltonian problem is the quantum analog of max-sat. A Hamiltonian is a Hermitian matrix acting on quantum states, thus it is for a system of n qubits. A k-local Hamiltonian is a Hamiltonian which can be written as the sum of Hamiltonians, each of which act non-trivially on at most k qubits. The k-local Hamiltonian problem, which is a promise problem, is defined as follows. The input is a k-local Hamiltonian acting on n qubits, which is the sum of polynomially many Hermitian matrices that act on only k qubits. The input also contains two numbers, such that for some constant c, the problem is to determine whether the smallest eigenvalue of this Hamiltonian is less than A or greater than B. Promise that one of these is the case. The k-local Hamiltonian is QMA complete for K2. QMA hardness results are known for even simplistic and physically realistic lattice models of qubits such as where represent the Pauli matrices. Such models are applicable to universal, adiabatic quantum computation. The Hamiltonians for the QMA complete problem can also be restricted to act on a two-dimensional grid of qubits or a line of quantum particles with 12 states per particle. Other QMA complete problems. A list of known QMA complete problems can be found at http://arxiv.org/abs/1212.6312. Related classes. QCMA, which stands for Quantum Classical Merlin Arthur, is similar to QMA, but the proof has to be a classical string. It is not known whether QMA equals QCMA, although QCMA is clearly contained in QMA. QIP, which stands for Quantum Interactive Polynomial Time, is a generalization of QMA where Merlin and Arthur can interact for k rounds. QMA is QIP. QIP is known to be in PSPACE. QIP is QIP where k is allowed to be polynomial in the number of qubits. It is known that QIP equals QIP. It is also known that QIP equals IP equals PSPACE. Relationship to other classes. QMA is related to other known complexity classes by the following relations. The first inclusion follows from the definition of NP. The next two inclusions follow from the fact that the verifier is being made more powerful in each case. QCMA is contained in QMA since the verifier can force the prover to send a classical proof by measuring proofs as soon as they are received. The fact that QMA is contained in PP was shown by Alexei Kitaev and John Watrous. PP is also easily shown to be in PSPACE. It is unknown if any of these inclusions is strict. It is not even known whether P is strictly contained in PSPACE or P equals PSPACE.